All right, welcome to part one of our lecture video series for Friday, April 21st, where we talk about something called specific heat capacity, hereby indicated by C lowercase s. So if we're going to have a conversation about specific heat capacity, we should probably remind ourselves about what we know about heat Q in general. So as a refresher, remember that heat is the amount of thermal energy that is transferred as a result of there being some temperature difference between our system and surrounding. So what you and I perceive as heat is really just a thermal energy that is being transferred from the heat source to your surroundings that you're perceiving because there is some change in temperature. So like when you hold a warm mug of coffee, right? The heat that you feel is a result of thermal energy being transferred from the coffee to your hand because of the initial change in or difference in temperature between the hot cup of coffee system and the kind of normal human body temperature of your surroundings. Sorry, Ziggy's freaking out. Get off the treadmill. He thinks he's an athlete today. So, why are we reminding ourselves about the definition of heat? So remember, heat ultimately relates to some change in temperature. And we came up with this relationship at the end of our lecture on Wednesday, where we determined that heat has some kind of direct proportionality to whatever that temperature difference is, delta T. Because as we increase the change in temperature, then we're going to increase the amount of heat that's exchanged across that temperature difference. And remember, directly proportional has a very particular mathematical structure, right? Directly proportional is always going to show our dependent and independent variables having a quotient that's equal to a constant. So for example, if I were just to think about this in terms of like algebra, when we think about directly proportional, we think about a linear system like y is equal to m times x, where m is the slope, which is a constant. And if I were to rearrange this particular expression so that I have my constant on one side and my variables on the other, I would see that y over x is equal to m. So because I've got a direct proportionality between my two variables, then I can say that their quotient is equal to a constant. So relating this back to heat and change in temperature, we see that heat in proportion with delta T is equal to some constant C, which we call the heat capacity of a substance. So this is one way to quantify heat, where we have heat capacity as being something that is a constant that is substance specific. And then remember, the definition of heat capacity is the amount of energy required to raise some material temperature by 1 degree centigrade. So this is just kind of like a little refresher of what we were talking about when it came to just heat. So this is where we landed on Wednesday from our little recall session. And we had this question that was, what other factors could affect something like heat or the amount of thermal energy transfer in a system? So I'm going to rephrase that question from Wednesday using language that we've seen from earlier in the class regarding intensive and extensive properties. So question: is heat an intensive or extensive property. So let's kind of refresh on these terms. So remember, heat is the amount of thermal energy across some temperature difference. So this is thermal energy. Transfer. And then we have these two different types of physical properties for a substance. The first is we have an intensive property. So just a reminder, intensive, internal, right? Interior, kind of meaning like within or inherent in a substance. So when we're talking about an intensive property, we're talking about a property that is independent of the amount, AMT, of a substance. So regardless of how much of a substance we have, that property is going to be the same. So think about density, right? I could have 100 grams of flour, I could have 100 tons of flour, but regardless, as long as that flour is packed in the same way, the density of flour is going to be the same. Same with water, right? If I had 1 milliliter of water versus 10 milliliters of water, regardless of my quantity, the density of water is the same at some given temperature. Compared to an extensive property, external, outward. So extensive properties, let me just darken this a little bit. This is a property that does depend on the quantity or amount of substance. So these are things like mass, volume. So let's think about this with regards to heat. So the thermal energy transfer. So we might say that temperature, like how much net energy that is thermal energy that is in a system, is intensive, right? Like it doesn't matter if I've got, I don't know, a swimming pool's worth of water or if I have an ocean's worth of water, as long as those systems of water have reached some kind of thermal equilibrium, meaning like they're the same temperature throughout, then we could say that temperature is an intensive property. So temperature is intensive. But what about heat? So remember, heat is not just temperature. It's the amount of thermal energy transfer as a result of there being some temperature difference. So let's think about this example of like, I don't know, a cup full of water. We got a little drinking glass full of our nice, refreshing, not distilled water, because remember, distilled water is non-electrolytic because it does not contain any dissolved ions. That's why it tastes gross. So this is just tap water. Versus if I were to go to the ocean, that is absolutely what this blue squiggle means, is we are at the ocean. So I might think about temperature, like some, I don't know, let's say initial temperature, an intensive property of both of these substances as being, I don't know, let's call them both at 20 degrees Celsius. However, what about heat? Meaning, will these different amounts of water have different amounts of energy transfer, specifically thermal energy transfer, in the face of some temperature change. So let's say that I wanted to bring both of these systems, my glass of water and my ocean, to some final temperature of 40 degrees centigrade. Is it going to be equally as energetically feasible to heat the glass of water from 20 to 40 degrees centigrade as it is to heat the ocean from 20 to 40 degrees centigrade? Like, which of these, if either, is going to have a harder time transferring thermal energy? So as you and I might know, just from kind of cooking, right? If we were trying to boil some water for pasta and we were being super lazy, we would probably boil like the minimum amount of water that's possible, like, I don't know, a single cup. And we would do that because we have an innate understanding that it takes less effort, less time, in order for us to boil that single cup of water compared to like an entire full pot of water. So what I'm getting at here is that heat is actually extensive. It depends on how much you have of any particular substance, right? Because if I'm trying to transfer heat out of my system or pump heat into my system, like I'm suggesting we do here, then how that system goes from its initial thermal energy to now its final new thermal energy is going to be inherently dependent on how many things I have to heat. And when I say things in chemistry, we're talking about molecules. So how do we incorporate this into our quantification of heat? How do we incorporate the idea that heat itself is extensive or depends on how much of a substance you have? So instead of calculating heat as we have up here, where we just use the heat capacity of a substance, which tells us how much energy is required to raise the temperature by 1 degree substance for a material, we use what's called the specific heat capacity, or C sub S. This is the amount of thermal energy that is required. I guess it could be any energy, right? We can heat a system using not thermal energy, but specific heat capacity is the amount of energy that is required to raise or change, I guess. It doesn't always have to be like actually making something warmer. So to change the temperature of a substance, specifically of 1 gram of that substance by 1 degree centigrade. So the difference here is that heat capacity is going to be given in joules per degree C, right? There is no mention in the unit for heat capacity of quantity of the substance. But now here with specific heat capacity, I see that we have this inclusion of quantity, meaning we're acknowledging the fact that it requires different amount of energy transfers to change the temperature of different substances that have different volumes or quantities. So how does this affect our equation for heat now that we're including a mass component? So let's look at the units of specific heat capacity. So this is still our proportionality constant that relates heat and our change in temperature, but the units are now in joules per, instead of degrees Celsius, per gram degrees Celsius. So the amount of energy in joules that is required to change the temperature of 1 gram of substance by 1 degree Celsius. And if I'm going to set this equal to some proportionality of Q and my change in temperature, that is, remember this direct proportionality, what I'm going to have to include now is something that relates to my mass. In fact, we're going to just include a mass in grams here. So let's rewrite this. We now see that the specific heat capacity of a substance is equal to Q over m delta T. This is how I like to think about how to quantify heat. However, this doesn't give us, because this tells us like all the relationships between things, right? It says that the amount of heat is directly proportional to the amount of substance you have in mass and the amount of temperature change you have. But if we rewrite this to solve for heat, we now see that heat Q is equal to m times C sub s times delta T, or you will see this written as MC delta T, although I do want you to be careful because C sub s is the specific heat capacity, which includes the extensive idea of heat, whereas C, heat capacity, does not. So I am going to be a little kind of picky on this unit here. So this equation, Q equals MC delta T, this is kind of the more realistic heat equation. So we have two different ways of quantifying heat. We can use it based on heat capacity or specific heat capacity. Either is fine. It just depends on what you're talking about. However, in this class, we are almost always going to be using this form because we do care about the different quantities of substances that are present perhaps in a chemical reaction or even just present in general if we're looking at some kind of chemical system. So there Ziggy goes. That's my cue to stop talking for now. I will see you in part 2, where we look at now calculating heat based on this new equation that involves the specific heat capacity.